So how do you know you're looking at a telescopic series then? Well, partial fractions is a good indicator, right? So if we start each series out with kind of running through that Rolodex in our minds, n-term pregnancy test first, right? And then if that is inconclusive, then we move on. Is it geometric? Okay. Is it harmonic? If it's not, then okay. Is it collapsing? Did we just find the sum? We found the sum, didn't we? So if I tell you find the sum, it's either geometric or telescopic. That's it, right? Can't be harmonic, right? Harmonic diverge. So anytime I say find the sum, you're one of those two, geometric or telescopic. How about this one? Oh, yeah. Sum n equals 2 to infinity, natural log of n over n minus 1. Now, I started this sum at 2, right? And that's okay. I mean, we need to start getting used to the idea that this can be different values. I know when we started out the whole idea of sequences, I always said n's going to start at 1, right? But as we proceed through here, n is going to be allowed to change, all right? It'll be a subtle thing that we kind of slowly do, but this is the first time you're seeing it. All this means is just, start at 2, right? Just plug in 2, then plug in 3, then 4, then 5, then 6. So, first of all, let's figure out what happens if we just do the n-term test. So take the limit as n goes to infinity of that. So what do you get? So you get infinity over infinity, L'Hopital, you get 1, right? Natural log of 1 is 0. Test fails, right? Yes? Limit of that is 0. Test fails. Move on. Geometric? I don't see like 4 to the n or things raised to the n, do you? Okay. Harmonic was definitely not a constant over n or something like that, right? So that's not harmonic. So the only other thing we have on the plate is telescopic, yeah? So what did we do last time? We did partial frame. What do you mean? Split the natural log? Yeah. Yeah, we can turn that into subtraction, can't we? We could do natural log of n minus natural log of n minus 1. Couldn't we? We could do that. Yeah, sure. That's allowed. Now, I'm going to do that. That's what we're going to do. But I want to show you, if we just were to start writing out the series to start, like if we said, hey, let's just look at this. What happens if I plug in 2? I get natural log of 2 over 1, okay? And then I do plus natural log of 3 over 2. And then I do plus natural log of 4 over 3, right? Plus, and that's what I would keep doing, right? There is no collapsing happening here. Do y'all see why there's no collapsing? I mean, there's no subtractions. So you're never going to get it to collapse unless you use the property of logs to rewrite this log as natural log of this minus this. Now start plugging in and let's see what happens. This is equal to what? Natural log 2 minus natural log 1, right? That's the first thing you'd get. And then plus natural log 3 minus natural log 2. Plus natural log 4 minus natural log 3. Plus natural log 5 minus natural log 4. Plus dot, dot, dot. Do y'all see the canceling happening here? It's a little easier on this one to see the canceling, I think. First guys kill off second guys 1 down. Right? Not 3 down this time. First guys kill off second guys 1 down. First guy kills off second guy, 1 down. First guy kills off second guy, 1 down. First guy kills off second guy, 1 down. So the only thing that is not touched here is what? ln1, which is 0, right? So the answer is 0? No. No, now you have to set up the nth partial sum. Okay, you have to set it up. You have to take the limit at the end. Who wants to volunteer to not do that on the test? Anyone want to volunteer now? Because I know someone's going to do it. No?
No promises.
Okay. Yeah. All right, so now we realize that there's some collapsing happening, right? We realize things are going to start canceling out. We just got to make sure that the tail end, the other side of the bridge, doesn't contribute to the sum. All right, we just need to make sure of that. So now we set up our nth partial sum. So the nth partial sum will be equal to natural log 2 minus natural log 1. Plus natural log 3 minus natural log 2 plus natural log 4 minus natural log 3. I don't need all these damn parentheses. I don't know why I'm using them. Okay, plus dot 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 plus, now let's go to the very end. What's the very last one I have? Natural log of n minus natural log of n minus 1. Right? That's the very last one I'd have. What's the one right before it? Natural log of n minus 1 minus natural log of n minus 2, because we have to take 1 away from each of those. Do I need to go any further? I mean, I could, but I can see the canceling right here. Questions? Sure. Let me run through this canceling out again. First guy, second guy, 1 down. This guy stayed. First guy cancels with second guy, 1 down. Right? So this is gone, this is gone, this is gone, this is gone. Is the natural log 4 gone? Yes. First guy cancels with second guy, 1 down. So that's in the dot, dot, dot. Now how about working backwards? First guy cancels with second guy, 1 down, right? But there is no 1 down. So this guy's staying. This guy gets canceled over here with that guy, right? How about this one? That's going to get canceled with something down there, right? So what stays here? Natural log of n, right? So our nth partial sum is negative natural log of 1 plus natural log of n. And what am I supposed to do with that? Take the limit. What is the limit as n goes to infinity of negative natural log of 1 plus natural log of n?
I got a question.
Yes.
Before we go on.
Yep.
I'm struggling to see why the ln of n doesn't cancel. Like, how come that doesn't reappear?
The pattern that we have established is that if you were the first guy inside of the parentheses, you will cancel with the second guy in the parentheses 1 down.
Right.
So if you're first, you've got to cancel with someone that's that way.
And it started with the ln of 2.
Uh-huh. Okay, and then this one, there's something over there, right? And then this one, he's a first one, there's something over there. But when you get down to this guy, we stopped the sum, so there's nothing down there for it to cancel with.
ln of n plus 1. If it were
Yeah, there would have been n plus 1 down there,
not before.
but not before. Yeah. So this is our sum right here. This is the limit we need to take. So natural log of 1 is 0. Okay, so that's just 0. But what's the limit as n goes to infinity of that? It's infinite. It's infinite. It's infinity, which means it diverges. This series diverges. diverges. Do you see the danger now? Do you see the danger? If you don't do this step, if you had just done this step and never went and looked at that stuff at the end, you would have told me the answer is what? Negative 0 or 0, right? Natural log of 1 is 0. So you would have said, oh, this thing adds up to be 0. That would have been wrong. Yes?
So like for like a real world application, like how would a computer use this to like what kind of data would be analyzed like this kind of like sum or series or
I'm not the only one, see?
No, they're great questions. But you know that I've been asked this question, obviously. We had a conversation about this last week. I have a pretty good answer, right?
Yeah.
But it takes a little bit of time. I mean, we can talk about it, but
I'm just asking because like it just helps me visualize what like
Dude, you and me.
yeah.
it's not one of those like
That's
why
the
do
same
we need
question.
this?
No, I know you're not asking that, but I mean, it's just there's so many things that
It could be applied to.
yeah. I mean, it's just anytime you type something into your calculator is using a series. It's not using anything other than addition, subtraction, right? And that's the thing about series. Series is just a bunch of addition and subtraction, right? That's all it is.
I have it here if you want.
No. Do you have time after class? Okay, we can talk after class about that. Yeah. It's just the amount of material we have. Here, I'll give you this. I'll put this out there for you. Just as kind of like a carrot in front of the rabbit. Have you ever seen this? Have y'all ever seen that before? Yes? No? So this is argued, it's debatable, that this is called the most beautiful equation in math. All right? And beauty is subjective, right? So I think we could all argue that. But a lot of people think it is the most beautiful equation in math. And the reason why is because it puts together all of the most important numbers in math. And it's true. It's a true equation. So, obviously pi is something we've been dealing with, right? E is something we've been dealing with. I is the imaginary number, right? And now 1 and 0 may not seem that big of a deal, but 1 and 0 are actually very important numbers in our number system. 1 is called the multiplicative identity, so it has the property that if you multiply it by any number, it stays the same. So 4 times 1 is still 4, right? That seems trivial, but in order to qualify as what's called a field, our number system must have a multiplicative identity. And the multiplicative identity for our number system is 1. And 0 is the additive identity. Every field must have an additive identity, and ours is 0. 4 plus 0 is 4. So these numbers are super important, and this equation brings it all together, right? So I'll prove this later. I'll have to use series to do it, though, all right? So I'll actually show you that this is true. All really I'm going to have to show you is this. I'm going to have to convince you that this is -1, right? If I convince you of that, you'd be happy? Because if that's -1, then -1 plus 1 should be 0. So I'm going to actually prove this is true. All right? Hang tight. Well, you got to believe it's valuable. Okay, so we've got basically the idea of telescopic there. Yeah? Eight three. The integral and comparison tests. So let's take a look at a specific series to get us motivated here. Well, you know what? Let's make that n cubed. All right, let's run through the quick Rolodex here. Is anybody offended by me using pregnancy test? It's 2019, so I have to be real careful. Is that offensive to anyone? Maybe somebody's going through something right now.
I just think it's funny that all the guys in here like are talking about pregnancy tests. Like y'all have.
I'm the only guy talking about pregnancy tests. You can't blame anyone else but me. That's why I want to make sure that I'm not being offensive. Okay, you sure? All right. So sad. So sad. 2019 is so sad. All right, 1 over n cubed. Is this going to fail the nth term test?
Yeah.
It's going to fail, right? That obviously goes to 0, so we got to move on. Geometric? N's not in the exponent, right? So it's not geometric. Harmonic? It's not linear, right? It's cubed, so it's not linear down there. Telescopic. Partial fractions, you're not going anywhere with partial fractions, right? I mean, how are you going to factor n cubed? It's just n cubed, right? So you can't rewrite that as anything that's going to be worth it for us. So we are kind of stuck at this point, right? There's nothing we have so far. Agreed? All right, so the integral test. What do you think that has to do with? Doing an integral somehow, right? Somehow bringing in an integral. Okay, so let's take a look at this. Let's take a look at this sequence. Take a look at this sequence. A sub n is 1 over n cubed. The sequence, not the series, the sequence. So if I plug in 1, what do I get? Plug in 1, I get 1. And I have a dot there, right? When I plug in 2, I get 1/8. So it's gotten small really fast, right? Here. And then if I plug in 3, it's even smaller, right? Okay. So that's the sequence. It starts to dive down to 0 very quickly. Now, the series is us adding those up, right? Isn't it us just adding those up? So what if I do this? What if I were to like measure the height from here to here? Right, that's 1, yes? And what if I took that and drew a line to the side and straight down like that? Then I create this rectangle, right? And then wouldn't the area of that rectangle be the same as the height of that point in terms of numeric value? So what I'm saying is the area of this should be equal numerically to the height of this right here. How wide is it? 1, right? So if this is 1 unit high, 1 times 1, that's 1. What about the next one? Well, how tall is it? 1/8, but how wide is it? 1. So the area of that's 1/8, and so is its height, yes? So if I'm trying to add up this series right here, I'm trying to do 1 plus 1/8 plus, and I keep going, right? Well, I guess I could write it down. 1/27 plus dot, dot, dot. If I'm trying to add those up, it's that height plus that height plus that height, but I could also look at it as being the sum of those areas, yes? And what does the integral do? It gets us areas, right? Now the integral is not defined on a sequence though. You can't have an integral on a sequence. You have to have a what? A function, a curve, right? So imagine I were to, instead of putting this up here, what if I were to graph this? If I graph that function of x, and I just do it on the interval 1 to infinity, then wouldn't it be that right there? Yeah? And then wouldn't the integral from 1 to infinity of that function give us that area under there? Yes?
Doesn't that technically require us to take the limit so that it can be f of n?
Limit?
Because it has
Limit.
to let f of n equal that function right there, so you can take the limit of it.
What limit are you referring to?
Never mind.
I mean, because we do have a limit if we do, this is an improper integral. So we have one of the endpoints goes to infinity, so we do need a limit, but I'm not sure that's what you were saying. Were you thinking about L'Hopital and how you have to make it a function? Okay. Okay, so look, all I'm trying to get you to see right now is that when we're trying to add this up right now, we don't have a way to do it, right? But if we were to look at the sequence as dots and then draw rectangles from those, then the area of the rectangles is connected in some manner to the area. Am I saying that they're the same? Absolutely not. Right? I'm not saying they're the same. But I'm saying that they're connected to one another. Like this area, the area in red, in this case, is smaller than this area, isn't it? And this one's smaller. But they're going to stay close to one another. The areas should be within some scalar factor of one another. Like the area of this rectangle can't be infinite if this red one's not infinite. Does that make sense? Like if this box here is finite, then that red area is finite, and it works the other way around. If the red area is finite, then that box must be finite. So this leads us to what's called the integral test. And we're not going to get into the proof of the test because it's a little harder to prove why the test is true all the time. But it's on your sheets, which I brought those sheets last class, right? But I didn't bring one for everyone because I was hoping you would go print your own. So I expect everyone has that today. And if you don't, then you better next time, okay? This is our tests. So do you see on here the integral test? Do y'all see the integral test? So it says here that you have a sum, n equals 1 to infinity. Here you go. You've got this infinite series. And what we're going to do is we're going to look at our sequence as a function. All right? So this is us changing it so that we can look at it as an integral. Okay? So it says here that this will converge. Okay, converges. So this right here converges when? Converges if the integral from 1 to infinity of our function of x dx converges, and diverges if the integral from 1 to infinity diverges. Now, I'm leaving out something very important right now, but let's just understand this. If we're ever looking at a series and we're having trouble with it, if we look at the sequence inside, right? If we look at that sequence inside and look at that as a function of x, then if we can integrate it on the number line from 1 to infinity, if we can do that integration and get an answer that's convergent, then we know that the series converges. If it's divergent, then the series diverges. So it's like whatever the integral does, the series does. Whatever they do together. Okay? But there's one huge kind of caveat, little star asterisk at the bottom that you didn't read. And it's over here on the side. What does it say? The function f obtained, right, from the sequence must be what? Continuous, positive, decreasing, and integrable. Okay, so what does continuous mean? We basically draw it without picking up our pencil. What does positive mean? Always above the x-axis. What does decreasing mean? It has to basically go down to 0, right? It's going to be headed towards 0. And what does integrable mean? We can find the antiderivative of it, right? Okay, so let's check this. I would like to see if we can do this with an integral test. So integral test. So first thing, let's define the function. Let f of x be equal to 1 over x cubed, right? And we're going to define it on what interval? 1 to infinity. Why are we not going like to 0? I mean, obviously it wouldn't be defined, but the sequence starts at 1, right? The sequence. So we're going to start ours at 1. Yes?
Earlier you had one that started at 2. If that was the case, do we have
Did I, what? Oh, if this started at 2?
Yeah.
Yes.
So does that have to be 2?
We would make it 2. All right, we good? Now, let's check. Let's check. Is this continuous? F continuous. This is a question. On that interval it is, yes? I mean, obviously it's not defined at 0, but on that interval it's continuous. What's the next thing we need?
Positive.
Is it positive? Is f greater than 0? I think that's pretty easy for us to just say yes, because we're plugging positive numbers in, and 1 over a positive number cubed is still positive, right? So I think that can be said, but you have to show it, okay? On the test, if you're going to use the integral test, you better show me that you thought about this, all right? You have to. Okay, what's the next condition we need? Is it decreasing? Well, is it decreasing?
Yes.
Convince me.
If you plug it in 1, 2, 3, 4, 5, and 6, the fractions are getting smaller.
Smaller?
The fractions are getting bigger, but the number itself is getting smaller.
What do y'all think? Is that acceptable? I think logically that makes sense. I mean, if you start plugging in numbers, they get smaller. Unfortunately, there are some functions that don't behave like that, though. They'll get bigger initially, and then they'll start getting smaller or something like that. So here's the way we can show it's decreasing. Ready? Here's how we show it. So is f decreasing? Question mark? Well, here's what I'm going to do. I'm going to take a look at its derivative real quick. What's the derivative of that function? That's a derivative, right? And what can you tell me about this derivative? No matter what value you ever plug in for x, what can you tell me about that derivative? It's always negative, right? You have a negative number on top of a positive number. That's always negative. And what can you tell me from Cal 1 about a function if its derivative is negative? It's decreasing, right? That's the way you can check if a function is decreasing. You just take its derivative and show it's negative. That's more convincing than anything else, all right? Questions on that derivative? Okay, so check, it's decreasing. Any other things we have to check? Well, can we integrate that? I hope so. I hope so. Okay, so here we go. We're going to integrate. So we integrate from 1 to infinity of 1 over x cubed dx, which is the same as the limit as t goes to infinity of integral 1 to t of x to the negative 3 dx. So all I'm doing here is I'm realizing this is an improper integral back from an earlier section. We replace the infinity with t. We take the limit as t goes to infinity, rewriting 1 over x cubed as x to negative 3. Now I'm going to find the antiderivative. That's just power rule, right? So what is the antiderivative of that? What is it? Negative 1/2 x to the negative 2. Right? And we're going to be evaluating that from where to where? 1 to t, right? Yeah. Questions? This is limit. T goes to infinity. I'm going to rewrite it. Negative 1 over 2 x squared evaluating 1 to t. All right. So now what we'll do limit t goes to infinity. All right, we're going to have two things. We plug in t, we subtract, we plug in 1. Right? What is it? It's 1/2, right? This is 1/2. That's 1/2, right? Right? So, let's come back. What is that? Converges. That's it. 1/2 has nothing to do with it. Okay? We're not saying that this adds up to be 1/2. We're saying it converges. That's all we can say. Can't say what it converges to. All right? I said this a couple of classes ago, that we're just going to be asking, does it converge or diverge? There's a few series where we can actually tell you what it converges to. Geometric, telescopic. Those are about it. Other than that, it's just going to be convergence or divergence. In this case, the integral test leads us to a conclusion that the integral converges. That means the series converges. Remember, when I drew the picture, we had area and then we had these rectangles, right? These aren't the same values. Like the sum of the rectangles is not the sum of the area, or is not the area. They're off. But what I can tell you is that if this is finite, then so is that. And if that's finite, it converges. Make sense? Okay. How about this? All right. So you break out the nth term test first. You let n go to infinity, top goes to infinity, bottom goes to infinity, right? Bless you. L'Hopital, right? Run L'Hopital, you get 1 on top, you get e to the n again on the bottom. So run that limit, you get 0. Tells you nothing, you move on. Geometric.
Yes.
Well, kind of, right? We have e to the n here, right? So it's looking kind of geometric, but this n is not part of geometric, right? Like if this were a number, like 4, then yes, this would be geometric. But because that's not, we can't, right? And if you really don't like it, I make it n squared, and then maybe you'd really be convinced that it's not. Right? So not geometric. Harmonic? No way. Telescopic? Well, you would have to be able to rewrite this somehow where you get subtractions in between things. And we don't have partial fractions, and it's not a log. Log allowed us to rewrite. Otherwise, no. Yes?
You said if it was a 4, like instead of
If that was a 4 up there, then...
4.
Oh, yeah, sorry. 4 is just the constant 4. Then it would be geometric. So we're running out of options here, right? So integral test. Next. Integral test. So can we rewrite that as a function? Sure, right? F of x equals x over e to the x. Can we define that on the interval 1 to infinity? Sure. Is that continuous on this interval? Yes. Right? It's continuous. What else? Positive? Is it positive? Well, we're plugging in positive numbers, right? So positive over e to anything is positive, so that's positive, right? Next thing, decreasing, right? This one I might need to look at. Decreasing, I can do that real quick by taking a derivative, right? What is the derivative of this? What rule are you using here? You could use quotient rule, right? Derivative of the top times the bottom. So derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. Yeah, we took Cal 1. We took Cal 1, right? Okay, so there's your quotient rule on that. Is that always negative? Well, why don't we factor out an e to the x on top?
We just have X in there.
What's that? Do y'all agree? That's always positive, right? That's always positive. 1 minus x is always going to be negative if x is bigger than or equal to 1, right? Well, at the worst case, if x is 1, what do we get? 0, so maybe our derivative's flat there. But as soon as we go past 1, what? We know that the function's going to start diving down because my derivative is going to be negative. Make sense? So check, I'm good. Check with decreasing. And is it integrable? Well, I don't know. That depends on you. Can you integrate it? Can you integrate that?
I mean, the denominator isn't going to change. You take the integral. You could do.
We're not going to integrate the top and bottom separately, right? Please don't do that at this point. You're not going to be like x squared, like 1/2 x squared over e to the x. You're not going to do that, please. Please. Please don't do that on a test. Integration by parts. This is integration by parts. That's what was said, right? I would rewrite it like that and then do integration by parts. Ultraviolet minus voodoo, all that fun stuff. Okay, in an effort to save us time, and the fact that I feel like you could all do that. Excuse me. Integrate what?
Yeah, that's not actually
X.
what I meant.
What?
When I said that.
What? What did you say?
That taking the integral of the denominator wasn't going to change.
Oh, top and bottom separately?
Yeah, I wasn't.
No, I know you weren't saying that. Yeah, no, I'm just saying please don't do that. No, I wasn't referring to you at all. X over, okay, so from 1 to what? Infinity. Boy, it really wants me to pay. It converges. It converges to 2 over e. So after you go through your integration by parts, you'll get a nice number as an answer, and that means that it converges. That means the original series converges. Okay? Yeah, so I'm not going to have time in class to do this, but if you do this integral, you should get 2 over e. And that's enough for you to say it converges. All right. So how's this feeling so far? I mean, we're still getting into it. If you look at this chart here, if you look at everything, we've got nth term test, right? Yay. Geometric series, got that. Integral, we've got that, right? We still need what? P series, comparison, ratio, root, alternating series, and then the last one. So absolute value. So there's still a ways to go, right? But on this test, we're going to stop at geometric, right? That's where we're going to stop. I mean, sorry, harmonic, right? Yes? Yeah, no, are we officially behind now? I think we are. Yeah, no. Today is, wow, we're so, like, how does this happen? How does this happen? I spend way too much time on 8.1. That's what happens. But I feel like it's such an important section because that's where you're first starting to use the notation for sequences. Yeah, don't worry about 8.3 and 8.4. Well, 8.4 for sure, no. 8.3, there's only certain problems you can do in 8.3. It's not on the test. Yeah, so only up through harmonic. Okay, Wednesday's test, you have the topics that were sent to you. Any questions about the test other than show us the test? How many questions? I don't have it written yet, so. But I just basically went through those topics, should give you a good indication. All right. Study your homework. Is it cold outside yet? I guess none of us know yet. It's not cold? Is it delayed? I thought it was coming here at noon.